Space is often described as beautiful, and it absolutely is. Those photographs from our most powerful telescopes show us swirling galaxies painted in shades of purple and gold. Nebulae that look like cosmic flowers blooming across thousands of light years. Stars scattered like diamonds on black velvet. But here is something we do not talk about quite as often. Space can also be deeply unsettling. Not in the way a horror movie is unsettling, with jump scares and monsters hiding in the dark. No, space disturbs us in a more profound way. It disturbs us because of scale, because of power, because of forces so immense that our minds genuinely struggle to wrap around them. Tonight, we are going to explore the most formidable objects that astronomers have discovered out there in the cosmos. We are going to look at things that make our most powerful nuclear weapons look like tiny firecrackers. We are going to examine objects so dense that a single teaspoon of their material would weigh as much as a mountain. We are going to discuss phenomena that could theoretically sterilize entire galaxies of all life in a matter of seconds. But here is the thing. This is not meant to keep you up at night with worry, because as we explore each of these cosmic phenomena, we are also going to talk about the reality of our situation here on Earth. We are going to look at the actual chances of any of these things affecting us. And spoiler alert, in almost every case, those chances are incredibly, wonderfully small. Before we dive in, let me say something about the nature of fear itself. When we were evolving on the African savannas, our ancestors learned to fear certain things: predators, heights, darkness, the rustle of grass that might conceal a lion. These fears kept us alive. Our brains developed circuits dedicated to recognizing threats and responding to them. But the cosmic phenomena we will discuss tonight are of a completely different character. They operate on scales of distance and time and energy that our ancestors never encountered. Our fear circuits do not really know what to do with them. How do you feel genuine dread towards something a billion light years away? How do you emotionally process an explosion that releases more energy in 10 seconds than the sun does in 10 billion years? You cannot, really. And that is okay. What we can do is appreciate these phenomena intellectually. We can understand their power, marvel at their strangeness, and let them expand our sense of what is possible. So settle in. Get comfortable. We are about to take a journey through the darker side of astronomy. Think of this journey like a gradual descent into the cosmic deep end. We will start with our own star, which, despite being the source of all life on Earth, can occasionally throw tantrums that affect our technology. Then we will move outward to the stellar remnants in our galaxy, the crushed cores of dead stars that produce magnetic fields and gravitational forces beyond anything we can create on Earth. We will examine the invisible wanderers that drift silently through the darkness between stars. We will look at the giant black holes that sit at the centers of galaxies, including our own. We will witness the most powerful explosions the universe has to offer, and eventually, we will contemplate the very fabric of reality itself and what might happen if it were to change. Let us begin with something close to home. We have a star right in our neighborhood, and while the sun is generally well behaved, it occasionally has outbursts that can reach us directly. These are not the most dramatic phenomena we will discuss tonight, but they happen frequently enough and close enough to actually affect our daily lives. A coronal mass ejection, or CME, is a massive burst of plasma and magnetic field released from the sun's corona, its outer atmosphere. These events happen when built-up magnetic energy is suddenly released. Billions of tons of charged particles are thrown out into space at speeds of up to several million miles per hour. When a CME is directed at Earth, It can reach us in 1 to 3 days. When it arrives, it interacts with Earth's magnetic field. This interaction can compress and distort our magnetic shield. It can drive electrical currents through the upper atmosphere. And it can have real effects on our technology. In 1859, a massive solar storm known as the Carrington event struck Earth. Named after the astronomer Richard Carrington, who observed the solar flare that preceded it, this event remains the most powerful geomagnetic storm in recorded history. Telegraph systems across Europe and North America failed. Some telegraph operators received electrical shocks. Telegraph papers caught fire spontaneously from the induced currents. And auroras, normally visible only near the poles, were seen as far south as the Caribbean and Hawaii. People in the northeastern United States could read newspapers by the light of the aurora alone. In 1859, our technology was primitive by modern standards. The telegraph was the most advanced electrical system we had. A similar event today would be far more disruptive and far more costly to recover from. A Carrington-level event in the 21st century could damage power grids around the world. Transformers could be destroyed, leading to blackouts lasting weeks or months. Satellites could be damaged or disabled. GPS navigation could become unreliable. Communication systems could fail. The economic damage has been estimated in the trillions of dollars. In July of 2012, Earth narrowly missed a CME of Carrington-level intensity. It crossed Earth's orbit about a week after we had passed that point. If it had arrived a week earlier, we would have experienced a direct hit. The good news is that we are aware of this threat and taking steps to prepare. We have satellites monitoring the sun that can give us hours of warning before a CME arrives. We are developing more resilient power grids. We are learning how to protect satellites and other vulnerable infrastructure. There is perhaps a 12% chance per decade of a Carrington-level event, which sounds alarming, but our preparation improves every year. Our star follows an approximately 11-year cycle of activity, with periods of maximum and minimum solar activity. During solar maximum, CMEs are more common and more intense. During solar minimum, the sun is relatively calm. We are able to predict this cycle to some degree, which helps us prepare for periods of heightened risk. There is also something called a superflare. Some stars produce flares that are tens, hundreds, or even thousands of times more powerful than anything our sun has produced in recorded history. We have observed these superflares on other sun-like stars. The question of whether our sun could produce such an event is still being debated. There is some geological evidence that the Earth has been hit by powerful solar events in the distant past. But these events are rare enough that they should not be a major concern. What CMEs really illustrate is the dynamic nature of stars. We sometimes think of the sun as a constant, unchanging presence in the sky, but it is actually a churning ball of plasma with complex magnetic fields that twist and snap and reconnect. It has weather, in a sense, and sometimes that weather reaches all the way to Earth. The physics of coronal mass ejections is intimately connected to the sun's magnetic field. This magnetic field is generated by a dynamo process in the interior, where the combination of convection and differential rotation creates complex magnetic structures. These structures can become tangled and twisted, building up energy over time. When the magnetic stress becomes too great, the field can suddenly reconfigure, releasing energy in a flare and often launching a CME. The ejected plasma carries the magnetic field with it, creating a bubble of magnetized material that propagates outward through the solar system. The interaction of a CME with Earth's magnetic field is complex. The orientation of the magnetic field within the CME determines how strongly it will couple with Earth's field. If the CME's field is oriented opposite to Earth's field, the coupling is stronger and the geomagnetic effects are more severe. This is why predicting the impact of a CME is challenging. We can detect a CME when it is launched from the Sun, but we cannot easily determine the orientation of its magnetic field until it arrives at Earth. Space weather forecasters use models and observations from spacecraft to estimate the likely impact, but there is always uncertainty. The effects of geomagnetic storms extend beyond power grids and satellites. Navigation systems that rely on the ionosphere, including some aircraft navigation, can be disrupted. Radio communications at certain frequencies can be affected. Pipelines can experience induced currents that accelerate corrosion. Even astronauts on the International Space Station need to take shelter during strong solar events. There is also a biological dimension. The increased radiation from strong solar events can pose risks to astronauts and airline passengers flying at high altitudes over the poles. Some studies have suggested correlations between geomagnetic activity and various biological effects on Earth, though these remain controversial. The historical record of solar storms is incomplete, but there is evidence of events even larger than the Carrington event in the distant past. Ice cores and tree rings preserve records of solar activity extending back thousands of years. Analysis of these records suggests that extreme solar storms, perhaps 10 times stronger than Carrington, occur every few thousand years. Such an extreme event would be devastating to modern technology. The economic damage could be in the tens of trillions of dollars. Recovery would take years. Some have argued that preparing for such an event should be a national and international priority. The good news is that awareness is growing. The National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center, which monitors solar activity and issues forecasts and warnings. International cooperation through organizations like the World Meteorological Organization helps coordinate the global response to space weather. Some power grid operators have begun installing equipment to protect transformers from geomagnetically induced currents. Satellite operators have developed procedures for protecting their spacecraft during strong solar events. These measures will not prevent all damage from a major storm, but they will reduce the impact. Now let us venture further out, to objects that operate on entirely different scales of power. Imagine you could take our Sun, this massive ball of burning hydrogen that dominates our entire solar system, and squeeze it down. Keep squeezing until all that mass, all that material, is compressed into a ball roughly the size of a city. Not a big city either. Something like Manhattan, maybe 15 miles across at most. What you would have is called a neutron star. And neutron stars are already among the strangest objects we know about. They are so dense that a sugar cube of neutron star material would weigh about 1 billion tons. They spin so fast that some of them rotate hundreds of times per second. They are the crushed cores of massive stars that exploded as supernovae, and they represent matter pushed to its absolute limits. But magnetars are neutron stars that have gone even further into strangeness. They are neutron stars with magnetic fields so powerful that they break our normal understanding of what magnets can do. Let me try to put this in perspective for you. You probably have some magnets around your house, maybe some on your refrigerator. Those magnets have a magnetic field strength of roughly 100 Gauss. That is a unit scientists use to measure magnetic fields. 100 Gauss is strong enough to hold up a piece of paper with a little note on it. An MRI machine at a hospital, one of the most powerful magnets most people will ever encounter, has a field strength of about 10,000 to 30,000 Gauss. That is strong enough that medical staff have to ensure you have no metal on your body before you go in. People have been seriously injured when metal objects flew across the room toward an MRI machine. A magnetar has a magnetic field of up to 1 quadrillion Gauss. That is a 1 followed by 15 zeros. It is roughly 1,000 trillion times stronger than Earth's magnetic field. At the distance of the Moon from Earth, roughly 240,000 miles, a magnetar's magnetic field would be strong enough to erase every credit card on our planet. It would wipe clean every hard drive, corrupt every piece of magnetic storage. And that is from the distance of the Moon. Get closer, say 1,000 miles from a magnetar, and the magnetic field would be strong enough to distort the electron clouds around atoms in your body. The chemistry that keeps you alive would stop working. Not gradually, instantly. Get closer still, and the magnetic field would stretch atoms into long, thin tubes aligned with the field lines. Matter as we know it would stop existing in any recognizable form. Now, here is where I can put your mind at ease quickly. We know of about 30 magnetars in our galaxy, and the closest is over 10,000 light-years away. At that distance, even a massive flare causes no problems for Earth whatsoever. These objects are genuinely well beyond any realistic concern for us. But that safety does not make them less fascinating to study. On August 27th, 1998, a magnetar called SGR 1900 plus 14, located about 20,000 light-years away, experienced a flare. The radiation was bright enough to ionize Earth's upper atmosphere. It actually affected our planet's ionosphere for several minutes. Think about that. Something 20,000 light-years away reached out and touched our atmosphere. On December 27th, 2004, another magnetar, SGR 1806-20, had an even larger flare. This one released more energy in 1/10 of a second than our Sun produces in 250,000 years. Several satellites were temporarily blinded by the radiation. Inside a magnetar, the magnetic field is so strong that it affects the shape of atoms themselves. The electron clouds around atomic nuclei become elongated, stretched into cigar shapes, aligned with the magnetic field lines. Light passing through such a region behaves strangely, with different polarizations traveling at different speeds. Scientists have calculated that if you could somehow survive near a magnetar, you would see double images of everything. Scientists have used magnetars to test fundamental physics in ways that would be impossible in any laboratory on Earth. The strong magnetic fields provide natural laboratories for studying how matter and light behave under conditions we could never replicate. Some magnetars have been used to test theories about how nuclear matter behaves at extreme densities. There is also an ongoing effort to understand how magnetars form in the first place. Not every neutron star becomes a magnetar. In fact, most do not. Something special has to happen during the collapse of the massive star, something that amplifies the magnetic field to those incredible levels. One leading theory involves the dynamo effect. In the few seconds after the neutron star forms, before its interior solidifies, the hot, dense matter is in a state called convection. Hot material rises and cooler material sinks, creating circulating currents. If these currents are vigorous enough, they can amplify any initial magnetic field to magnetar levels. Magnetars also fade over time. The intense magnetic field decays, releasing energy that heats the surface of the star. Young magnetars are hotter and more active than older ones. Eventually, after tens of thousands of years, the magnetic field weakens to the point where the object is no longer classified as a magnetar, but as a regular neutron star. How do we even study something that extreme without getting anywhere near it? That is one of the remarkable achievements of modern astrophysics. Through careful analysis of the radiation they emit, the timing of their pulses, and the effects of their flares, we have pieced together a detailed picture of these objects. We will never visit one. We do not need to. The discovery of magnetars happened gradually. For years, astronomers observed certain neutron stars that seemed to behave strangely. They emitted more X-rays than they should have based on their rotation. They had occasional bursts of gamma radiation that did not fit the patterns of other known phenomena. It was only in the 1990s that scientists began to piece together the idea that these were neutron stars with extraordinarily powerful magnetic fields. The name magnetar was coined in 1992 by Robert Duncan and Christopher Thompson, who developed the theoretical framework for these objects. Their work predicted many of the properties that were later observed, including the giant flares that can briefly make a magnetar the brightest gamma-ray source in the sky. One of the most fascinating aspects of magnetars is how the magnetic field affects the space around them. In normal circumstances, a vacuum is just empty space. But near a magnetar, the magnetic field is strong enough to affect even the vacuum itself. Quantum electrodynamics predicts that in sufficiently strong magnetic fields, the vacuum becomes birefringent, meaning that light of different polarizations travels at different speeds. This effect has actually been observed in radiation from magnetars, providing confirmation of some of the strangest predictions of quantum theory. There is also ongoing research into what happens to the crust of a magnetar during a flare. The surface of a magnetar is made of a crystalline lattice of nuclei, held in place by the intense magnetic field. When the field suddenly rearranges, it can crack this crust, releasing enormous amounts of energy. Understanding these starquakes could tell us about the properties of matter at nuclear densities. Scientists have even proposed using magnetars as cosmic laboratories for testing physics beyond the standard model. Some theories predict that exotic particles might be produced in the extreme magnetic fields around magnetars. By searching for the signatures of these particles in magnetar radiation, astronomers might be able to test theories that cannot be tested in any Earth-based laboratory. Black holes are probably the most famous formidable objects in space. You have almost certainly heard of them. They are regions where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. They are places where our normal understanding of space and time breaks down completely. But here is something you might not have thought about. The black holes we hear about most often are the ones we can actually detect, the ones at the centers of galaxies, the ones that are actively swallowing matter and releasing great amounts of radiation, the ones that announce their presence loudly across the cosmos. What about the quiet ones? What about black holes that are not eating anything at the moment? What about black holes that are just drifting silently through space, invisible in the darkness? These are called rogue black holes, or wandering black holes. Let me explain how these things come to exist. When very massive stars die, they can collapse into black holes. This is a normal part of stellar evolution, nothing unusual about it. But sometimes, this collapse happens asymmetrically. The explosion that accompanies the formation of the black hole can give the newborn black hole a kick, sending it flying off in some random direction at high speed. Other times, black holes can be ejected from their homes through gravitational interactions. If two black holes in a binary system encounter a third black hole, the gravitational dance between them can fling one or more of them out into space at tremendous velocities. The result is a black hole that is no longer anchored to any particular location. It just drifts through the galaxy through interstellar space, through the void between stars, invisible, silent. What makes rogue black holes genuinely unnerving is that we cannot see them directly. A black hole by itself, one that is not actively consuming matter, emits no light. It is literally a hole in space. The only way we can detect such an object is through its gravitational effects on things around it. If a rogue black hole passes near a star, it might bend the light from that star in a detectable way through a phenomenon called gravitational lensing. If it passes through a cloud of gas, it might start consuming that gas and briefly become visible. But in the emptiness between stars, a rogue black hole could pass within a few light years of us, and we might never know it was there. So how many of these things are out there? Based on the number of massive stars that have formed and died throughout our galaxy's history, astronomers estimate that there could be anywhere from 10 million to 1 billion stellar mass black holes wandering through the Milky Way. 1 billion in our galaxy alone. Now, stellar mass black holes are not enormous. They typically range from about 3 to a few dozen solar masses. Their event horizons might only be a few miles across, and space is staggeringly empty. The average distance between stars in our region of the galaxy is about 4 light years. The average distance between rogue black holes, even if there are a billion of them, would still be thousands of light years. The solar system is 4.5 billion years old, and in all that time, no rogue black hole has disrupted our planetary orbits enough to render Earth uninhabitable. There is something philosophically interesting about rogue black holes. They represent indifference on a cosmic level. A rogue black hole does not care about anything. It has no purpose, no direction, no goal. It simply drifts, following the laws of physics, affected by the gravitational pulls of whatever massive objects it happens to pass near. If a rogue black hole were to encounter our solar system, it would not be malevolent. It would not be attacking us. It would just be continuing along its path, utterly unaware that it was causing any disruption. In some ways, this is more unsettling than a deliberate threat. A monster in a horror movie can potentially be reasoned with, fought, or escaped. A rogue black hole cannot be negotiated with. It does not care. It simply is. And there is something beautiful about our ability to even conceive of rogue black holes. We cannot see them directly, yet we can deduce their existence from our understanding of physics. We can estimate their numbers, predict their behavior, and calculate their effects. Our minds have reached out into the darkness and mapped what cannot be seen. In recent years, astronomers have begun to detect rogue black holes through a technique called astrometric microlensing. When a black hole passes between us and a distant star, its gravity bends the light from that star. This causes the star to appear to shift position slightly as the black hole moves across our line of sight. By carefully measuring these tiny shifts, astronomers can detect the presence of an otherwise invisible black hole. In 2022, astronomers announced the first unambiguous detection of an isolated stellar mass black hole using this technique. The object, located about 5,000 light-years away, has a mass of about 7 solar masses. It is drifting through space at roughly 45 kilometers per second, probably having received a kick from the supernova that created it. This detection was exciting not because it revealed anything unexpected, but because it confirmed what we had long suspected. Rogue black holes are out there. They are real. And we are finally developing the tools to find them. The black hole detected in 2022 is just the tip of the iceberg. As our instruments improve and our surveys expand, we will likely discover many more of these dark wanderers. Each detection will help us understand the population of stellar remnants in our galaxy and the violent processes that created them. Some scientists have proposed that rogue black holes might occasionally capture small objects into orbit around them. A rogue black hole passing through a dense stellar region might gravitationally capture asteroids or even small planets. These captured objects would orbit the black hole in lonely trajectories, circling an invisible master in the darkness between stars. There is even speculation about whether advanced civilizations might use rogue black holes as power sources. The energy released by matter falling into a black hole is more efficient than nuclear fusion. A civilization that could navigate to a rogue black hole and harness its gravity might have access to enormous amounts of energy. This is highly speculative, of course, but it illustrates how even the darkest objects in the universe might serve purposes we have not imagined. Are there frozen worlds out there that once orbited stars like ours, now drifting alongside these invisible wanderers? We will explore that thought later, when we discuss rogue planets. But first, let us look at black holes of a very different scale. We just talked about stellar mass black holes, the ones formed from dead stars, typically a few times to maybe a few dozen solar masses. But the universe has a taste for going big. And when it comes to black holes, things can get very, very big indeed. At the center of nearly every large galaxy, including our own Milky Way, lurks something called a supermassive black hole. These are black holes that have grown to almost mind-boggling sizes. We are not talking about 10 solar masses. We are talking about millions or even billions of solar masses, all compressed into a single region of space. Let me tell you about the one at the center of our galaxy. It is called Sagittarius A star, often written as Sagittarius A with an asterisk. It sits about 26,000 light-years away from Earth, right at the heart of the Milky Way. Sagittarius A star has a mass of roughly 4 million suns. Its event horizon, the point of no return, is about 14 million miles across. That is roughly the distance from our Sun to the orbit of Mercury. If you placed Sagittarius A star where our Sun is, Mercury's entire orbit would be inside the event horizon. And here is the strange thing. 4 million solar masses sounds huge. It is huge. But compared to some other supermassive black holes out there, Sagittarius A star is actually pretty modest. The supermassive black hole at the center of the galaxy M87, the one that was photographed by the Event Horizon Telescope in 2019, has a mass of about 5.4 billion suns based on the most recent measurements. That is more than 1,000 times more massive than our own galaxy's central black hole. But even that is not the record holder. The most massive black hole we have discovered so far is at the center of a galaxy called TON 618. This one weighs in at roughly 66 billion solar masses. Its event horizon is larger than our entire solar system. If you placed it where the Sun is, it would swallow everything out to far beyond the orbit of Pluto. 66 billion suns, all in one object. There is something fascinating about what happens near the event horizon of a supermassive black hole. Time itself behaves differently there. According to Einstein's theory of general relativity, gravity affects the passage of time. The stronger the gravity, the slower time passes relative to an observer far away. Near the event horizon of a supermassive black hole, time slows dramatically. If you could somehow survive and hover just outside the event horizon, watching someone far away, you would see them moving incredibly fast. Their entire lifetime might pass in what feels like minutes to you. Conversely, they would see you moving in extreme slow motion, seemingly frozen in place. At the event horizon itself, from the perspective of a distant observer, time appears to stop completely. Light from an object falling into a black hole gets stretched and dimmed as the object approaches the event horizon. The object never quite seems to cross the boundary from the outside perspective. It just gets dimmer and dimmer and redder until it fades from view entirely. From the perspective of the falling object, however, the crossing of the event horizon happens in finite time. The unlucky traveler would pass through and continue falling toward the singularity. What happens at the singularity is one of the great unsolved problems in physics. Our equations break down there. Now, Sagittarius A is 26,000 light-years from Earth. At that distance, its gravitational influence on our solar system is essentially zero. We are orbiting the center of the galaxy, yes, but that is a gentle, stable orbit that takes about 230 million years to complete. We have made this trip roughly 20 times since Earth formed, and the orbit is not getting any closer to the central black hole. What makes supermassive black holes particularly interesting is their relationship with their host galaxies. Scientists have discovered tight correlations between the mass of a central black hole and the properties of its galaxy. More massive galaxies tend to have more massive black holes. The stellar velocities in the central regions of galaxies correlate with black hole mass. This suggests that black holes and galaxies co-evolve. They grow together. The black hole affects how the galaxy forms, and the galaxy affects how the black hole grows. It is a cosmic partnership that spans billions of years. Some scientists even argue that supermassive black holes are essential for galaxy formation. In the early universe, the intense radiation from actively feeding black holes may have helped regulate star formation, preventing galaxies from forming too many stars too quickly. The black holes acted like thermostats, controlling the temperature and behavior of the gas in their host galaxies. So these cosmic giants are not just consumers of matter, they are also sculptors of the galaxies they inhabit. The correlation between black hole mass and galaxy properties is one of the most important discoveries in modern astronomy. It tells us that the story of galaxies and the story of black holes are intertwined in ways we are only beginning to understand. There is ongoing research into how supermassive black holes grow. In the nearby universe, we see black holes that are mostly quiet, like Sagittarius A. They are not consuming much matter. But in the distant universe, we see quasars and active galactic nuclei, supermassive black holes that are actively feeding and growing. The transition between these states is not fully understood. What causes a quiet black hole to become active? What shuts off the feeding and returns a black hole to dormancy? These questions are at the frontier of astrophysics. One possibility is that galaxy mergers play a role. When two galaxies collide, their central black holes eventually merge as well. But before they merge, the chaos of the collision can funnel large amounts of gas toward the center of the combined galaxy, feeding the black holes and potentially triggering quasar activity. Another possibility is that secular processes within galaxies can occasionally direct gas toward the center. A bar structure in a spiral galaxy, for example, can channel material inward over millions of years. When enough gas accumulates near the central black hole, it might trigger a period of activity. Astronomers are also interested in the smallest supermassive black holes. The smallest ones we have found are about 100,000 solar masses. But how do black holes grow from stellar masses of tens of solar masses to supermassive scales of millions or billions, there should be intermediate mass black holes, objects with thousands or tens of thousands of solar masses bridging this gap. Yet these intermediate mass black holes have proven elusive. Finding them would help us understand the early stages of supermassive black hole growth. In 2019, the Event Horizon Telescope produced the first direct image of a black hole, showing the shadow of the supermassive black hole in M87 against the bright glow of its accretion disk. This image was a triumph of international collaboration, combining data from radio telescopes around the world to create an Earth-sized virtual telescope. In 2022, the Event Horizon Telescope released an image of Sagittarius A itself, our own galaxy's central black hole. This image was more challenging to create because Sagittarius A is much smaller and more variable than the black hole in M87. The turbulent matter around it changes on timescales of minutes, whereas the larger M87 black hole changes over days. These images do not show the black hole itself, of course. The event horizon is by definition the point from which no light escapes. What we see is the shadow of the black hole, the dark region where light has been captured, surrounded by the bright ring of superheated matter orbiting just outside. If magnetars are notable for their incredible magnetic fields, and black holes for their gravity, then gamma-ray bursts deserve attention for their sheer, overwhelming intensity. These are the most powerful explosions in the universe since the Big Bang, and until a few decades ago, we had no idea they existed. The story of how we discovered gamma-ray bursts is actually kind of fascinating. During the Cold War, the United States launched a series of satellites called the Vela satellites. Their job was to detect the gamma radiation that would be released by nuclear weapons tests. The military wanted to make sure the Soviet Union was not secretly testing bombs in space. Starting in 1967, these satellites started picking up gamma-ray signals. But they were not coming from Soviet weapons tests. They were coming from all directions in space. Brief flashes of gamma radiation, lasting anywhere from milliseconds to several minutes, appearing randomly from random locations in the sky. For years, no one knew what these things were. When the information was finally declassified in the early 1970s, astronomers were baffled. What could produce such intense bursts of gamma rays from so far away? Over the following decades, we gradually figured it out. Gamma-ray bursts come in two main varieties. Short gamma-ray bursts last less than 2 seconds. Long gamma-ray bursts last longer than 2 seconds, sometimes for several minutes. Short gamma-ray bursts are produced when two neutron stars collide, or when a neutron star collides with a black hole. Two objects, each with more mass than the Sun compressed into a space the size of a city, smashing together at a significant fraction of the speed of light. The result is a brief, intense flash of gamma radiation. Long gamma-ray bursts happen when a very massive star dies in a particular way. The core of the star collapses into a black hole, and as material falls into the newly formed black hole, two jets of matter and energy blast out along the axis of rotation. These jets punch through the outer layers of the dying star and stream out into space at nearly the speed of light. If one of those jets happens to be pointed at Earth, we see a gamma-ray burst. The light is focused by the jet, making it incredibly bright. The most powerful gamma-ray burst we have ever recorded was called GRB 221009A, detected in October of 2022. It was located about 2 billion light-years away. Even at that distance, It was bright enough to temporarily blind the detectors on some of our satellites. It released more energy than scientists thought was physically possible for such events. Models had to be revised to account for it. Unlike supernovae, which spread their energy out in all directions, gamma-ray bursts focus their energy into narrow jets. This means that if one of those jets were pointed at Earth from close enough, it could strip away the ozone layer on the side of Earth facing the burst. Without the ozone layer, ultraviolet radiation from our own star would become deadly. How close is close enough? Astronomers estimate roughly 5,000 to 10,000 light-years, depending on the power of the burst. Some scientists have even proposed that a gamma-ray burst might have caused one of the major extinction events in Earth's history. The Ordovician-Silurian extinction, which happened about 445 million years ago and killed off roughly 85% of marine species, has some characteristics that are consistent with a gamma-ray burst. The killing was selective in ways that suggest intense ultraviolet radiation from above. We cannot prove that a gamma-ray burst caused it, but we cannot rule it out either. The reassuring context is this: gamma-ray bursts are rare. In a galaxy the size of the Milky Way, we estimate that a long gamma-ray burst happens maybe once every few 100,000 to few million years. Most massive stars that could produce them are found in regions of active star formation, which our solar neighborhood is not. And even if a suitable star were to explode within range, the jets would have to be pointed almost exactly at Earth to be dangerous. Those jets are narrow, typically only a few degrees wide. There are a couple of stars we keep an eye on. Eta Carinae is a massive, unstable star about 7,500 light-years away. It could potentially produce a gamma-ray burst when it finally explodes. But based on its orientation, any jets it produced would not be pointed at Earth. WR104 is a Wolf-Rayet star about 8,000 light-years away. For a while, astronomers were concerned that its jets might be pointed at us. More recent measurements suggest we are probably not in the firing line, but we continue to watch it. The physics of how gamma-ray burst jets form and propagate is still being studied. We know that the jets punch through the outer layers of the dying star, emerging at nearly the speed of light. But the details of how the jet maintains its coherence, how it accelerates particles to such high energies, and how it produces the specific spectrum of radiation we observe are still not fully understood. One interesting aspect of gamma-ray bursts is the afterglow. After the initial burst of gamma rays, which might last only seconds, there is a longer period of emission at lower energies. X-rays, optical light, and radio waves can be observed for days, weeks, or even months after the initial event. This afterglow is produced as the jet collides with the surrounding material and slows down. By studying the afterglow, astronomers can learn about the environment around the dying star. They can determine how much material was ejected, how fast it is moving, and what elements it contains. What else might those distant flashes tell us about the early universe? They are being used as cosmic probes, their light carrying information about the matter it passed through on its journey to Earth. Every burst is a message from the distant past. The most distant gamma-ray burst ever detected, GRB 090423, occurred when the universe was only about 630 million years old. The light from this explosion traveled for over 13 billion years to reach us. When it was emitted, the first galaxies were just beginning to form. By studying the spectrum of this ancient light, astronomers can learn about the conditions in the early universe. The light passes through intergalactic gas clouds on its way to us, and each cloud leaves its fingerprint in the spectrum. We can measure the composition of these clouds, their temperatures, and their densities. Gamma-ray bursts have also been proposed as a way to search for signs of advanced civilizations. If a civilization wanted to communicate across interstellar distances, they might use a beacon that mimics a natural gamma-ray burst, but contains encoded information. So far, we have found no evidence of such artificial signals, but the search continues. There is also interest in using gamma-ray bursts to test fundamental physics. The photons from a gamma-ray burst travel billions of light-years to reach us. If the vacuum of space has any structure at extremely small scales, as some quantum gravity theories predict, then photons of different energies might travel at slightly different speeds, over billions of light-years. Even a tiny difference would accumulate to a measurable delay. So far, no such delay has been observed. This puts constraints on theories of quantum gravity and tells us that space is very smooth at small scales. But the search continues with each new burst. The afterglow of a gamma-ray burst can also reveal the presence of dust in distant galaxies. Dust absorbs and scatters light, leaving characteristic signatures in the spectrum. By studying afterglows, astronomers can measure the dust content of galaxies when the universe was young, learning about the history of star formation and heavy element production. Some gamma-ray bursts have been observed to have multiple components, with different pulses arriving at different times. Understanding the origin of this variability is an active area of research. It might reflect the internal structure of the jet, or the interaction of the jet with the surrounding material, or variations in the central engine that powers the burst. The shortest gamma-ray bursts, lasting only milliseconds, are particularly mysterious. They might be produced by the merger of a neutron star with a very small black hole, or by some other exotic process. The brevity of these events makes them difficult to study, but they represent some of the most extreme phenomena in the universe. You probably know about regular supernovae. When a star more than about 8 times the mass of our Sun runs out of fuel, its core collapses. The outer layers bounce off the collapsing core and are blasted into space. The explosion is bright enough to briefly outshine an entire galaxy. That is already pretty impressive. But some stellar explosions make ordinary supernovae look modest by comparison. A hypernova is essentially a superpowered supernova. It occurs when the core of a very massive star collapses directly into a black hole. As we discussed earlier, this can produce jets that blast out at nearly the speed of light. A hypernova releases 10 to 100 times more energy than a regular supernova. It is often associated with long gamma-ray bursts. But there is an even more dramatic type of stellar explosion. It is called a pair instability supernova. The process works like this. Very massive stars, those with more than about 130 times the mass of our Sun, develop incredibly hot cores. We are talking about temperatures of several billion degrees. At these temperatures, something strange starts to happen. Normally, a star is held up against gravity by radiation pressure. The energy produced in the core pushes outward, balancing the inward pull of gravity. But at extreme temperatures, some of the gamma-ray photons in the core start converting into pairs of particles, specifically an electron and its antimatter partner, a positron. This process is called pair production. When this happens, energy that was supporting the star against gravity suddenly gets locked up in these particle pairs. The radiation pressure drops, and the star starts to collapse. As the star collapses, it heats up even more. Nuclear reactions run away. The core becomes a runaway thermonuclear bomb, and then the entire star explodes. Not just the outer layers, like in a regular supernova. The entire star. Every bit of it is blasted into space. In a pair instability supernova, nothing is left behind. No neutron star, no black hole, just an expanding cloud of debris containing all the material that once made up a star more than 100 solar masses. A pair instability supernova can briefly outshine an entire galaxy by orders of magnitude. It can remain visible for months or even years, and it can produce huge amounts of heavy elements, scattering them across space. We have observed a few candidates for pair instability supernovae. SN 2007bi is generally considered a confirmed example, extraordinarily bright and long-lasting. SN 2006gi, discovered in 2006, was incredibly luminous and remained visible for over a year. Some astronomers believe it was a pair instability supernova, though there is debate about whether it might have been a different type of event called a pulsational pair instability supernova. Stars massive enough to produce pair instability supernovae are extremely rare in the modern universe. They tend to form in regions of active star formation, which our solar neighborhood is not. The chances of such a star existing close enough to threaten Earth are essentially zero. These events mostly happened in the early universe, when giant stars were more common. The ones we observe now are in distant galaxies. But there is something valuable in studying these ancient explosions. Pair instability supernovae, when they occur, produce large amounts of a specific isotope of nickel called nickel-56. This radioactive nickel decays into cobalt and then into iron, releasing energy that powers the supernova's light for months. By studying the light curves of these events, how they brighten and fade over time, astronomers can figure out how much nickel-56 was produced. This tells us about the internal physics of the explosion. It helps us understand how nuclear reactions proceed under the most intense conditions. The early universe was full of pair instability supernovae. When the first generation of stars formed, they tended to be massive, very massive. Some may have been hundreds of solar masses. When these first stars died, many of them probably exploded as pair instability supernovae. These explosions seeded the early universe with heavy elements. Before these stars formed and died, the universe contained only hydrogen, helium, and tiny amounts of lithium. Everything else, every carbon atom in your body, every oxygen atom you breathe, every iron atom in your blood was forged inside stars and scattered by explosions like these. The pair instability supernovae of the early universe were particularly generous. They produced large amounts of heavier elements and dispersed them across huge volumes of space. Without these catastrophic deaths, the universe might never have accumulated enough heavy elements for rocky planets to form. Life as we know it might never have been possible. There is something philosophical to consider here. The most dramatic deaths of the most massive stars were also essential acts of cosmic construction. They were the universe building the toolkit needed for complexity, for chemistry, for life. This is a recurring theme in astronomy. The forces that destroy can also create. Supernovae that end stellar lives scatter the elements needed for planets and life. Black holes that consume everything nearby also help regulate star formation on galactic scales. The universe does not separate destruction and creation into neat categories. They are intertwined, part of the same cosmic cycle. The study of pair instability supernovae has accelerated in recent years thanks to wide-field surveys that scan the sky looking for transient events. Telescopes like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory are designed to detect supernovae and other explosive events in distant galaxies. When a candidate pair instability supernova is detected, follow-up observations with larger telescopes can characterize its properties. One of the goals of this research is to find pair instability supernovae at even higher redshifts, looking back to even earlier times in cosmic history. The first generation of stars, called population 3 stars, probably included many objects massive enough to explode as pair instability supernovae. Detecting these ancient explosions would give us a direct window into the very first stellar deaths. There is also interest in understanding the boundary between pair instability supernovae and other outcomes. Stars in a certain mass range might experience pulsational pair instability, where the pair production causes the star to eject material in a series of eruptions before finally collapsing. These events would have different observational signatures than complete disruption. And at the very highest masses, above about 260 solar masses, the energy released by pair production is not enough to unbind the star. Instead, these ultramassive stars would collapse directly to black holes without a bright explosion. The boundary between these different outcomes depends on the star's initial composition, rotation rate, and other factors that are still being studied. Earlier, we talked about supermassive black holes sitting at the centers of galaxies. We noted that our own galaxy's central black hole, Sagittarius A, is relatively quiet. It is not actively consuming large amounts of matter right now. But supermassive black holes are not always quiet. Sometimes they wake up, and when they do, they become the most luminous objects in the known universe. When a supermassive black hole is actively consuming large amounts of matter, it is called an active galactic nucleus. The matter falling into the black hole forms an accretion disk, superheated to millions of degrees, radiating intense light across the electromagnetic spectrum. A quasar is an especially luminous type of active galactic nucleus. The term comes from quasi-stellar radio source, because when they were first discovered in the 1960s, they looked like stars in photographs but emitted unusual amounts of radio waves. What makes quasars so extraordinary is their brightness. A single quasar can be more luminous than an entire galaxy. We are talking about something that outshines hundreds of billions of stars. All that light is coming from a region not much bigger than our solar system. The most distant quasars we have detected are over 13 billion light-years away. We see them as they were when the universe was less than 1 billion years old. And yet they are so bright that we can detect them from here. An object from near the beginning of time, so far away that its light has traveled for almost the entire age of the universe, and we can still see it. A typical quasar is powered by a supermassive black hole consuming matter at a prodigious rate. Some quasars consume the equivalent of several hundred Earth masses every minute. The matter spiraling into the black hole releases huge amounts of gravitational energy, which is converted into light, X-rays, and other radiation. Quasars also often produce jets. These are beams of particles and energy shot out perpendicular to the accretion disk at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the galaxy itself. And this is where blazars come in. A blazar is essentially a quasar whose jet is pointed almost directly at Earth. Because we are looking straight down the barrel of the jet, the light is boosted to even higher intensities through relativistic effects. Some blazars emit radiation at energies that are genuinely difficult to explain. They can vary in brightness dramatically over short periods, sometimes brightening or dimming by factors of 10 within days or even hours. Now, quasars are primarily found in the distant universe. They were much more common when the universe was young, when galaxies had more gas available for their central black holes to consume. The universe today is relatively quiet compared to those early times. Our own galaxy's central black hole could theoretically become more active if a large cloud of gas fell into it. But it would take a lot of material to turn Sagittarius A into anything resembling a quasar. And we are 26,000 light-years from the galactic center. Quasars have also been incredibly useful as cosmic lighthouses. Because they are so bright, we can see them at enormous distances. This makes them valuable tools for studying the universe between us and them. When light from a distant quasar passes through clouds of gas, that gas absorbs certain wavelengths of light. By studying the absorption patterns, astronomers can learn about the composition and distribution of matter across billions of light-years. Some quasars also act as gravitational lenses. Their enormous mass bends the light from even more distant objects behind them, magnifying and distorting that light. By studying these lensed images, astronomers can learn about both the quasar doing the lensing and the objects being lensed. The study of quasars has revolutionized our understanding of the early universe. We now know that supermassive black holes formed surprisingly quickly after the Big Bang. Some of the most distant quasars we have found are powered by black holes that had already grown to billions of solar masses when the universe was less than 1 billion years old. How these black holes grew so large so quickly remains an active area of research. One leading theory involves direct collapse black holes. In the early universe, under certain special conditions, massive gas clouds might have collapsed directly into black holes without first forming stars. These seed black holes could have been much larger than the stellar remnants that form from dying stars, giving them a head start on growth. Another possibility is that black holes grew through periods of super-Eddington accretion, consuming matter faster than the theoretical limit that would apply in normal circumstances. If the infalling matter is distributed in a certain way, it might be possible to circumvent the usual radiation pressure that limits accretion rates. Understanding early black hole growth is connected to understanding galaxy formation more broadly. The tight correlations between black hole mass and galaxy properties suggest that their growth is linked. Solving the puzzle of early black hole growth might also help us understand how the first galaxies assembled. Quasars have also taught us about the intervening universe. As quasar light travels to us, it passes through countless clouds of hydrogen gas. Each cloud absorbs light at a specific wavelength, creating a series of absorption lines in the quasar spectrum. This pattern, called the Lyman alpha forest, allows astronomers to map the distribution of hydrogen gas throughout cosmic history. The Lyman alpha forest reveals the cosmic web in exquisite detail. The density and spacing of absorption lines tells us about the distribution of matter along the line of sight. By observing many quasars in different directions, astronomers can build up a three-dimensional picture of the large-scale structure. Some quasars show evidence of outflows, powerful winds driven by the radiation from the accretion disk. These outflows can carry matter away from the galaxy at thousands of kilometers per second. Over cosmic time, such outflows can remove significant amounts of gas from galaxies, affecting their subsequent evolution. There is also a class of objects called changing-look quasars, which transition between quasar and non-quasar states on timescales of years or decades. These transitions are much faster than expected from simple models of accretion disk behavior. Understanding changing-look quasars might tell us about the physics of accretion disks and how they respond to changes in the fuel supply. Some researchers have speculated about whether quasars might pose any risk to life in their host galaxies. A newly activated quasar would suddenly flood its galaxy with intense radiation. Planets in the inner regions of the galaxy might experience dramatic increases in ultraviolet and X-ray flux. Whether this would be catastrophic for life or merely disruptive is uncertain. But it illustrates another way that the universe can be hazardous to complexity. Earlier, we discussed rogue black holes, invisible wanderers drifting through the galaxy. There are other wanderers too, ones that are not quite as exotic but perhaps even more thought-provoking. Rogue planets are worlds that do not orbit any star. They drift through interstellar space, alone in the darkness, warmed by nothing but the faint glow of distant stars billions of miles away. How do planets end up like this? Several ways, actually. Sometimes planets are ejected from their home systems through gravitational interactions. If a planet passes too close to a larger planet, or if a passing star disrupts the orbital dynamics of a system, a planet can be flung outward with enough velocity to escape its star entirely. It goes from being a world with seasons and a day-night cycle to being a frozen wanderer in the void. Other times, planets might form without ever having a star. In clouds of gas and dust where stars are forming, there are also smaller clumps that are not massive enough to ignite as stars. These might condense into planet-sized objects that were never bound to any star in the first place. How many rogue planets are out there? Some estimates suggest there could be more rogue planets in our galaxy than there are stars. We are talking about potentially hundreds of billions of sunless worlds drifting through the Milky Way. In 2021, astronomers announced the discovery of a population of rogue planets in a star-forming region about 520 light-years from Earth. They found between 70 and 170 of these objects, some of them several times the mass of Jupiter. This was just in one small region of the sky. Consider what it means to be a world without a star. On Earth, we take sunlight for granted. It warms our planet. It drives our weather. It powers photosynthesis, which produces the oxygen we breathe. Every food chain on Earth ultimately depends on sunlight. A rogue planet has none of this. Whatever warmth it has comes from within, from radioactive decay or leftover heat from formation. Over millions and billions of years, this internal heat would slowly radiate away into space. The planet would cool, and cool, and cool, until it was just a frozen ball of rock and ice drifting through the darkness at temperatures approaching absolute zero. Any atmosphere the planet once had would freeze solid. Any oceans would become ice. The surface would be utterly silent and utterly dark. But here is something interesting. Some rogue planets might not be completely dead worlds. A large planet with a lot of internal heat could potentially maintain liquid water under an icy crust for billions of years. If such a world also had moons with tidal heating, like Jupiter's moon Europa has, it could have subsurface oceans even without any star to warm it. Could there be life on a rogue planet? We genuinely do not know. It seems like a long shot. But biology has surprised us before with its ability to thrive in difficult environments. If intelligent life had once evolved on such a planet before it was ejected from its home system, imagine watching your star grow smaller and smaller over millennia as your world drifted away. Knowing that eventually the light would fade, the warmth would disappear. In the early days of our solar system, things were much more chaotic. Planets were still forming, still migrating, still interacting with each other gravitationally. It is possible, even likely, that there were more planets in our solar system at the beginning than there are now. Some of them may have been ejected during the early gravitational reshuffling. If that is true, then somewhere out there, drifting through interstellar space, there might be worlds that formed alongside Earth. Worlds that condensed from the same cloud of gas and dust. They would be frozen and dead now, of course, but they would still carry material from our solar system's birth. The planets that remained, including Earth, are the survivors of that early chaos. We are here because the gravitational dynamics allowed us to stay rather than be ejected. Now, what about wandering stars? Yes, there are stars that do not belong to any galaxy. They were ejected from their home galaxies through gravitational interactions, or they were torn away when galaxies collided, or they formed in the space between galaxies. These intergalactic stars are incredibly isolated. The nearest other star might be millions of light years away. Any planets around such a star would see a night sky that was almost completely empty, just the faint smudges of distant galaxies. Some estimates suggest that as much as half of all stars in the universe might be outside of galaxies, drifting in the spaces between galactic clusters. Astronomers are now developing techniques to detect rogue planets through gravitational microlensing, where the planet briefly magnifies the light of a background star as it passes in front of it. The signals are faint and brief, but with enough observations, we can estimate the population of these cosmic wanderers. Each detection is a small glimpse into the hidden majority of worlds that exist outside the warmth of stars. The search for rogue planets has revealed some surprising findings. Some of the objects detected are much larger than expected, several times the mass of Jupiter. These might not be planets at all in the traditional sense, but rather failed stars, objects that formed like stars but never accumulated enough mass to ignite nuclear fusion. The boundary between large planets and small stars is not entirely clear. Brown dwarfs, objects with masses between about 13 and 80 times that of Jupiter, confuse deuterium, but not regular hydrogen. They glow dimly with their own heat for billions of years. Some of the larger rogue objects detected might be brown dwarfs rather than planets. There is also interest in searching for Earth-sized or smaller rogue planets. These would be much harder to detect because their gravitational lensing signal would be weaker. But they might be even more common than the Jupiter-sized rogues. Some estimates suggest there could be trillions of rocky rogue worlds in our galaxy alone. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct a large-scale survey for rogue planets using gravitational microlensing. It is expected to detect thousands of these objects, giving us our first comprehensive census of the free-floating planetary population. What would happen if a rogue planet passed through our solar system? Probably nothing dramatic, unless it came very close. Space is mostly empty, and even a planet-sized object would be unlikely to directly encounter anything. But its gravity might perturb the orbits of comets in the outer solar system, potentially sending some toward the inner planets. There is speculation that a large planet, sometimes called Planet 9 or Planet X, might exist in the outer reaches of our solar system. Some astronomers have suggested that this hypothetical planet could be a captured rogue, a world that formed elsewhere and was gravitationally snagged by our star. This is not the most likely explanation for the orbital anomalies that have been attributed to Planet 9, but it illustrates how rogue planets might occasionally find new homes. The existence of so many rogue planets also raises questions about the formation and evolution of planetary systems. Our theories of planet formation focus on the processes happening in disks around young stars. But If planets are frequently ejected from their birth systems, we need to understand what causes these ejections and how they affect the systems left behind. Computer simulations suggest that gravitational interactions between growing planets can be quite chaotic. In the early stages of planetary system formation, planets can migrate inward and outward, sometimes crossing each other's orbits. When this happens, close encounters can scatter one or more planets into eccentric orbits or eject them entirely. The orderly solar system we see today might be the survivor of a more chaotic youth. We have talked about neutron stars when we discussed magnetars, but neutron stars have another trick, one that only gets revealed when two of them spiral together and collide. These events, called neutron star mergers, produce some of the most spectacular explosions in the universe. We call the resulting fireworks kilonovae. Consider how this happens. Sometimes, two neutron stars end up in orbit around each other. This can happen if two massive stars in a binary system both explode as supernovae, but stay gravitationally bound. The resulting pair of neutron stars slowly spirals together over millions or billions of years, losing energy through gravitational waves. Gravitational waves are ripples in space-time itself. When massive objects accelerate, they create these waves, which spread out through the universe at the speed of light. As a pair of neutron stars spirals together, it emits gravitational waves, which carry energy away from the system. This causes the orbit to shrink. The neutron stars get closer and closer. They spiral faster and faster, and eventually they collide. On August 17th, 2017, astronomers witnessed one of these collisions for the first time. Gravitational wave detectors on Earth picked up the signal of two neutron stars spiraling together. About 2 seconds later, telescopes detected a short gamma-ray burst from the same direction, and in the days that followed, astronomers observed the kilonova, the explosive aftermath of the collision. What happens in a neutron star merger is absolutely cataclysmic. Two objects, each with more mass than the Sun but only about 12 miles across, smash together at a significant fraction of the speed of light. The collision produces temperatures of billions of degrees. It throws out material in all directions, and it creates conditions so intense that heavy elements are forged in the explosion. Gold, platinum, uranium, and other heavy elements are produced in neutron star mergers. For a long time, scientists were not sure where these elements came from. Now we know that a significant fraction of the heavy elements in the universe, including the gold in any jewelry you might own, was produced in the collisions of dead stars. The kilonova that follows a neutron star merger is bright. Not as bright as a supernova, but still visible across intergalactic distances. It glows with a distinctive reddish color as the newly created heavy elements release energy. There is a poetry to this. The gold in a wedding ring was forged in the collision of two dead stars. The platinum in a car's catalytic converter came from a neutron star merger that happened billions of years ago. The uranium that powers nuclear reactors was created in some of the most cataclysmic events the universe has to offer. Scientists have calculated approximately how much of various heavy elements in the solar system came from neutron star mergers versus other sources. The picture is still being refined, but it seems clear that a significant fraction of elements heavier than iron originated in these collisions. Every time you hold a piece of gold or platinum, you are holding material from a cosmic cataclysm. Neutron star mergers produce a lot of dangerous outputs. They emit gamma rays, X-rays, ultraviolet radiation, and high-energy particles. They produce a short gamma ray burst, which could be dangerous if pointed at Earth from close enough. If a neutron star merger occurred within a few hundred light-years of Earth, and if the gamma-ray burst were pointed at us, it could damage our ozone layer and cause significant harm to life on Earth. But neutron star mergers are rare. We estimate that they occur maybe once every 10,000 to 100,000 years per galaxy, and they can only happen where there are neutron star binaries, which are not common in our neighborhood. There are no known neutron star binaries close enough to Earth to pose a threat. The 2017 detection opened a new era of astronomy. For the first time, we could study a cosmic event using both gravitational waves and light. This multi-messenger astronomy has already revealed secrets about the universe that neither method could uncover alone. It confirmed that neutron star mergers produce heavy elements. It provided new ways to measure the expansion rate of the universe, and it gave us a new window into the physics of matter under extreme conditions. The event in 2017, designated GW170817 after its detection date, was observed by thousands of astronomers using dozens of telescopes around the world. Within hours of the gravitational wave detection, telescopes identified the optical counterpart, a kilonova in a galaxy about 130 million light-years away. The kilonova faded over the following weeks, its light shifting from blue to red as different radioactive elements decayed. By modeling the light curve, scientists could estimate how much material was ejected and what elements were synthesized. The observations confirmed theoretical predictions that neutron star mergers are factories for elements heavier than iron. The detection also allowed astronomers to measure the speed at which gravitational waves travel. The gravitational wave signal arrived about 1.7 seconds before the gamma-ray burst. Since the source was 130 million light-years away, this tiny delay confirmed that gravitational waves travel at the speed of light to an extraordinary precision. This ruled out many alternative theories of gravity that predicted different speeds. Now, we are going to venture into more speculative territory. We have been talking about objects we have observed and phenomena we have detected. But there are also theoretical objects that might exist. Objects that we have not confirmed, but that physics suggests could be out there. One of these is strange matter. To understand strange matter, we need to talk briefly about what neutron stars are made of. Neutron stars are incredibly dense, made primarily of neutrons packed together so tightly that a teaspoon would weigh 1 billion tons. But neutrons are not fundamental particles. They are made of smaller particles called quarks. Specifically, a neutron contains 2 down quarks and 1 up quark. These are the 2 lightest types of quarks. But physics tells us there are actually 6 types of quarks in total. 2 of them, up and down, make up ordinary matter. The others, charm, strange, top, and bottom, are heavier and usually unstable. This is where things get interesting. Under extremely intense conditions, like those inside a neutron star, it might be possible for matter to convert into a form that contains strange quarks. This strange matter would consist of roughly equal numbers of up, down, and strange quarks. And according to some theories, strange matter might actually be more stable than ordinary matter. If strange matter is more stable than ordinary matter, then it represents a kind of lower energy ground state. Ordinary matter would be in a higher energy configuration. This leads to a disturbing possibility. If a piece of strange matter, called a strangelet, were to come into contact with ordinary matter, it might convert that ordinary matter into more strange matter, and the newly converted matter might then convert more matter. In principle, this process could continue until all the matter it touched was transformed. Sounds troubling, right? Straight out of science fiction. But here is the thing. We do not know if strange matter is actually stable. The theory that suggests it might be stable is called the strange matter hypothesis, and it is far from proven. Many physicists are skeptical. The mathematics is complicated, and we have no direct evidence that strange matter exists at all. This is very much a theoretical concern rather than an established threat. Furthermore, even if strange matter is stable, it might not be contagious in the way described above. There might be energy barriers that prevent ordinary matter from converting. The conversion process might be slow, or it might not work at all outside the incredibly intense conditions inside a neutron star. We have also never observed strangelets, despite looking for them. Cosmic ray detectors have searched for years without finding any convincing candidates. The Alpha Magnetic Spectrometer on the International Space Station has been looking since 2011 with no positive detections. Some scientists have even argued that if strangelets were stable and common, we would already have been converted long ago. The fact that Earth still exists, made of ordinary matter, is evidence that strangelets are either very rare, unstable, or non-existent. So strange matter and strangelets remain in the realm of theoretical concerns rather than confirmed threats. They are the kind of thing that makes for interesting scientific papers and thought experiments. What the strange matter hypothesis does highlight is how much we still do not know about the fundamental nature of matter. Even our best theories of particle physics have gaps and uncertainties. The universe may contain forms of matter we have not imagined yet. The standard model of particle physics, our best theory of fundamental particles and forces, has been spectacularly successful. It predicted the existence of the Higgs boson, which was discovered in 2012. It accurately describes countless experiments. But we know it is not complete. It does not include gravity. It does not explain dark matter or dark energy. It has many free parameters whose values are not predicted by the theory. Some physicists believe that a more complete theory might predict new states of matter that do not appear in the standard model. Strange matter is one possibility. There might be others. The interior of a neutron star, where densities exceed anything we can create in laboratories, might be the only place in the universe where such exotic states exist naturally. This is why neutron star observations are so valuable for fundamental physics. By measuring the masses and radii of neutron stars, by observing how they cool over time, by detecting the gravitational waves from their collisions, we can constrain the properties of matter at extreme densities. Every observation rules out some theories and supports others. The connection between astrophysics and particle physics has become increasingly important. Questions about the nature of dark matter, the behavior of matter at extreme densities, and the unification of forces all require input from both fields. The universe provides laboratories that we cannot build on Earth, and astronomers are learning to use them. We have saved one of the most mind-bending possibilities for near the end. This one comes from quantum physics, and it concerns the very fabric of our universe. To understand vacuum decay, we need to talk about the vacuum. In physics, the vacuum is not simply empty space. It is the lowest energy state of space. It is what you get when you remove all particles and fields. But even in this state, space has properties. The vacuum has an energy density. It has quantum fluctuations. It is not nothing. According to the standard model of particle physics, The vacuum we currently live in might not be the true lowest energy state. It might be what physicists call a false vacuum. A false vacuum is stable enough to exist for long periods, maybe billions of years. But it is not the most stable possible state. Think of it like a ball sitting in a small valley halfway up a mountain. The ball is stable there. It is not going to spontaneously roll anywhere. But below that valley, there is a deeper valley at the bottom of the mountain. If the ball could get over the ridge between them, it would roll down into the lower valley. If our universe is in a false vacuum, there is a possibility, however remote, that it could transition to a true vacuum. This transition would start at a single point and then expand outward at the speed of light. The bubble of true vacuum would consume everything in its path. The physics inside the bubble of true vacuum would be different from our physics. The fundamental constants that govern how matter and energy behave might change. Atoms as we know them might not be able to exist. Life would certainly be impossible. And because the bubble expands at the speed of light, we could never see it coming. We could never receive any warning. One moment we would exist, and the next moment we would not. The transition would be instantaneous from our perspective. Now, we do not know for certain that our universe is in a false vacuum. The question depends on precise values of certain physical constants, particularly the mass of the Higgs boson and the top quark. Our measurements suggest we might be right on the edge, in what physicists call a metastable state. But the uncertainty in our measurements is large enough that we cannot be sure. Current surveys of expert opinion suggest roughly even odds that we are in a false vacuum, but this is theoretical physics at its most speculative. Even if we are in a false vacuum, the probability of a transition occurring is inconceivably small. The universe has existed for nearly 14 billion years without transitioning. That suggests the false vacuum, if it is false, is extremely stable. And if vacuum decay were to occur, there would be nothing we could do about it. The bubble would travel at the speed of light. We could not detect it in advance. We could not escape it. We could not prevent it. If vacuum decay happened, we would not know it was coming. We would not see the bubble approaching. We would not have time to feel fear or regret. One moment, we would exist, living our lives, thinking our thoughts. The next moment, nothing, not even darkness. Just an absence of everything that was. Physicists sometimes talk about the anthropic principle, the observation that the universe seems fine-tuned for the existence of life. The fundamental constants of physics have values that allow for atoms, chemistry, stars, and planets. If those constants were slightly different, none of this would be possible. Vacuum decay represents the most dramatic version of this fine-tuning. Not only do the constants have to be right, but the vacuum itself has to be stable. If we live in a false vacuum, then our entire universe exists in a temporary state. Of course, borrowed time can be very long indeed. Even if we are in a false vacuum, the transition probability is so low that the expected timescale for decay might be vastly longer than the current age of the universe. We could have trillions of years ahead of us. Quadrillions. Numbers so large they lose meaning. Every moment that the universe continues to exist is evidence that the vacuum is more stable than the worst-case scenarios suggest. We have spent most of this documentary talking about objects, stars, black holes, planets, explosions. But some of the most thought-provoking aspects of space have to do with the large-scale structure of the universe itself and the vast empty regions between objects. When we look at the universe on the largest scales, we see something remarkable. Matter is not evenly distributed. Instead, it is arranged in a pattern that astronomers call the cosmic web. Imagine a three-dimensional network of filaments and nodes. The filaments are made of galaxies, gas, and dark matter, stretching across hundreds of millions of light-years. The nodes are galaxy clusters, regions where thousands of galaxies are grouped together, and between the filaments are voids, immense, empty regions where almost nothing exists. These cosmic voids are huge. The average void is about 150 million light-years across. Some are much larger. The Boötes void, discovered in 1981, is roughly 330 million light-years in diameter. If our Milky Way galaxy were at the center of the Boötes void, we would not have known other galaxies existed until the 1960s, when our telescopes became powerful enough to detect the faint smudges at the void's edge. What is inside these voids? Almost nothing. A few isolated galaxies here and there, but mostly just empty space. The density of matter in voids is perhaps 10 to 20% of the cosmic average. They are as close to true emptiness as the universe gets. If you were on a planet in one of those isolated void galaxies, the night sky would be almost completely dark. The nearest significant galaxy might be 100 million light-years away, a faint smudge barely visible to the most powerful telescopes. Any civilization in such a location would be profoundly isolated. They would look out and see almost nothing. They might not even realize that the universe contains other galaxies. They might think their small island of stars was all that existed. The voids themselves are not perfectly empty. They contain some galaxies, just far fewer than the filaments and clusters. These void galaxies tend to be smaller and bluer than average, still actively forming stars because they have not exhausted their gas supply. They are isolated, yes, but they are still part of the cosmic story. There is a concept in cosmology called the cosmic horizon. Because the universe is expanding, and because that expansion is accelerating, there is a limit to how far we can ever see or travel. Light from objects beyond a certain distance will never reach us, no matter how long we wait. Those objects are receding from us faster than light can travel. As the universe continues to expand, this horizon will shrink relative to us. Galaxies that we can currently see will gradually redshift and fade. Eventually, in the far future, observers in our local group of galaxies will look out and see nothing but blackness. All the other galaxies will have been carried beyond the cosmic horizon. The cosmic web, that magnificent structure of filaments and voids that we can see today, will be invisible to future astronomers. They will have no way of knowing that the universe was once filled with billions of galaxies. They might conclude that they live in an island universe, alone in an empty cosmos. Some have argued that we live in a special time in cosmic history, early enough that the universe is still active and interesting, late enough that we have developed the technology to observe and understand it. If we had arisen 1 trillion years from now, the sky would be dark and empty, and we would have no way to discover the true nature of the cosmos. This argument, sometimes called the cosmological window, suggests that there is a limited period in the universe's history when intelligent observers can learn about the large-scale structure. Too early, and the galaxies have not yet formed or been studied. Too late, and the accelerating expansion has carried them beyond the observable horizon. We happen to exist in this window. Whether this is coincidence or something more profound is a question that philosophers and scientists continue to debate. the anthropic principle suggests that observers will naturally find themselves in conditions compatible with observation. But it is still striking that our moment in cosmic time happens to be one when so much is visible and knowable. The study of the cosmic web has advanced rapidly in recent decades. Large galaxy surveys, like the Sloan Digital Sky Survey, have mapped the positions of millions of galaxies, revealing the filaments and voids in stunning detail. Computer simulations have reproduced the cosmic web using only the known laws of physics and the initial conditions from the cosmic microwave background. The agreement between simulations and observations is remarkable. We can watch virtual universes evolve from nearly uniform initial conditions to complex webs of structure, and they look like the real universe. This gives us confidence that we understand the basic physics of cosmic structure formation. But there are still mysteries. The nature of dark matter, which makes up most of the mass in the cosmic web, remains unknown. We know it exists because of its gravitational effects, but we do not know what particles comprise it. Numerous experiments around the world are searching for direct evidence of dark matter particles, so far without success. Dark energy, which is causing the accelerating expansion, is even more mysterious. It behaves like a constant energy density pervading all of space, but we do not understand its origin. Some theories connect it to the vacuum energy of quantum fields, but naive calculations give values that are vastly different from what is observed. The voids themselves are subjects of active research. Because they contain less matter than average, they expand faster than the filaments. Studying the distribution and shapes of voids can tell us about the nature of dark energy and the growth of structure. Some researchers have proposed that the voids might contain signatures of exotic physics. If there are additional dimensions of space, as some string theories predict, their effects might be more apparent in the low-density environments of voids. This is speculative, but it illustrates how the large-scale structure of the universe might encode information about fundamental physics. There is also interest in the objects that live in voids. Void galaxies evolve differently from galaxies in dense environments. They tend to be bluer, indicating ongoing star formation. They tend to be less disturbed, with more regular structures. Studying them helps us understand how environment affects galaxy evolution. The cosmic web is not static. It evolves over cosmic time, with filaments growing and voids expanding. By observing the web at different redshifts, we can watch this evolution in action. High redshift surveys are revealing the cosmic web as it looked billions of years ago, allowing us to trace its development. We have talked about dramatic objects and dramatic events, explosions, collisions, magnetic fields strong enough to scramble atoms. But the most profound thing about the universe might not be any single object. It might be where everything is heading. The universe had a beginning. Nearly 14 billion years ago, everything we can observe emerged from an incredibly hot, dense state. Space expanded, matter formed, galaxies assembled. Here we are, but the universe will also have an end. Not an explosion or a collapse, but something more subtle and more complete. As the universe expands, it cools. Stars burn through their fuel. New stars form at decreasing rates because the gas available is getting used up. Eventually, in tens of trillions of years, the last stars will burn out. No more fusion, no more starlight. The universe will still have black holes, but even black holes are not forever. Through a process called Hawking radiation, black holes slowly lose mass over incredibly long timescales. The largest black holes might last for something like 10 to the 100th power years, a number so large that writing it out would fill pages. But eventually, even they will evaporate. After the last black holes are gone, the universe will be left with the debris, particles scattered in an ever-expanding, ever-cooling void. The temperature will approach absolute zero. Nothing will happen. No structure will form. Energy will be so diffuse that no useful work can be done. This is called the heat death of the universe. It is not death by fire or ice, but death by uniformity. The technical term for this is thermodynamic equilibrium. In such a state, entropy has reached its maximum value. Entropy is a measure of disorder, and the second law of thermodynamics tells us that entropy in a closed system always increases or stays the same. It never decreases on its own. The universe, as far as we can tell, is a closed system, so its entropy is always increasing. Every process that happens, every chemical reaction, every nuclear fusion event in a star, every thought in a brain increases entropy. Energy flows from hot places to cold places. Concentrations disperse. Structure gradually breaks down. This is not something that can be stopped or reversed on a cosmic scale. Eventually, all the energy in the universe will be evenly distributed. There will be no hot spots and cold spots, no gradients to drive any processes, no way to do useful work, just a uniform bath of extremely low temperature radiation and widely dispersed particles. Some physicists have proposed even stranger possibilities for the far future. If protons decay, which some theories predict but has never been observed, then even the scattered matter would eventually disappear, leaving only radiation. If space continues to expand forever, eventually even the radiation will be so stretched and diffused that individual photons will be impossibly rare. The timescales involved are beyond comprehension. The last stars will burn out in about 100 trillion years. The last black holes will evaporate in something like 10 to the 100th power years. These numbers are so large that they lose all meaning. We cannot truly grasp them. But here is another way to think about it. The heat death is unimaginably far in the future. We are talking about timescales that dwarf the current age of the universe by factors of trillions of trillions. So much could happen between now and then. So much complexity could arise. And from a certain perspective, the fact that the universe can support complexity and life now is remarkable precisely because it will not last forever. This period, this cosmic moment when stars shine and planets form and life can evolve, is temporary. We are living in the interesting part of the universe's history. There have been various proposals for how civilizations might survive in a dying universe. Some involve extracting energy from black holes before they evaporate. Others involve migrating to regions where the local conditions remain favorable for longer. Still, others involve finding ways to slow subjective time so that the remaining energy lasts longer from the perspective of observers. These ideas are highly speculative, but they illustrate human creativity in the face of cosmic limits. We have only known about the heat death for about a century since thermodynamics was developed. In that short time, we have already begun to think about what it means and whether anything could be done. There is also the possibility that our understanding of physics is incomplete. The heat death is predicted by our current theories, but we know those theories are not the final word. Quantum mechanics and general relativity, our two most successful physical theories, are not fully compatible with each other. A future theory of quantum gravity might reveal new possibilities. Some speculative ideas involve the multiverse, the possibility that our universe is one of many. If new universes can form, perhaps through processes we do not yet understand, then the heat death of any individual universe might not be the end of existence in some broader sense. Other ideas involve the nature of information. In quantum mechanics, information is conserved, never truly destroyed. Even in a universe approaching heat death, all the information about everything that ever happened would still exist in some form, encoded in subtle correlations between particles. Whether this is meaningful from the perspective of observers is another question. More recently, cosmologists have explored the implications of dark energy for the far future. If dark energy behaves as currently observed, the accelerating expansion will eventually isolate galaxy groups from each other. But if dark energy changes over time, the far future could be quite different. Some models predict a big rip, where the accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms. Others predict a big crunch, where the expansion reverses and the universe collapses back to a hot, dense state. The ultimate fate of the universe is still uncertain. What we know is that our current cosmic era, with its stars and galaxies and complex chemistry, is temporary. We are living in the habitable epoch of cosmic history. The cosmic voids we discussed earlier, that structure of emptiness between the filaments of the cosmic web, are a preview of what the universe will look like in the far future. Empty, dark, silent. The filaments will stretch and thin, the galaxies will drift apart, and eventually, all of space will resemble those voids. So yes, the universe will eventually wind down, but that does not diminish what is happening right now. It makes it more precious. We have traveled through some of the most intense and formidable phenomena the universe has to offer. Objects so dense that a teaspoon weighs billions of tons. Magnetic fields strong enough to disrupt atomic chemistry. Explosions that dwarf anything in human experience. The possibility that the very vacuum of space could change states and destroy everything. And yet, here we are, on a small planet orbiting an ordinary star in a quiet arm of a spiral galaxy. The universe is genuinely dangerous. If we were in the wrong place, at the wrong time, any of these phenomena could end us in an instant. But we are not in the wrong place. Through cosmic accident, we ended up somewhere remarkably quiet, away from the galactic center, away from active star-forming regions, in a stable orbit around a well-behaved star. And we get to study these cosmic phenomena from that stability. We get to point our telescopes at them and figure out how they work. We get to satisfy our curiosity about the universe without being threatened by it. There is something remarkable about that, something deeply human. We are small creatures who evolved to worry about predators and find food and raise offspring. And yet, here we are, contemplating the physics of neutron stars and the eventual heat death of the universe. Our brains, which evolved for completely different purposes, turn out to be capable of understanding the cosmos. The phenomena we discussed put our human concerns in perspective. Whatever problems we face on Earth, we are not being threatened by magnetar flares or rogue black holes. Whatever conflicts divide us, they are small compared to the forces at play in the cosmos. And these phenomena are also beautiful. The swirling accretion disks of quasars, the explosive nebulae left behind by supernovae, the impossible density of neutron stars. These things represent the universe exploring its own possibilities, pushing matter and energy to their limits, creating structures that exist nowhere else in nature. There is a reason why astronomy has captivated humans for thousands of years. It is not just that the night sky is beautiful, though it is. It is that the stars represent questions. What are they? How far away are they? How did they form? What will happen to them? These questions have driven human inquiry since we first looked up and wondered. The answers we have found are more remarkable than any mythology. The stars are nuclear furnaces, fusing hydrogen into helium, releasing the energy that makes them shine. Some of them will die in spectacular explosions. Some will collapse into objects so dense that time itself bends around them. And in their deaths, they create the elements that make planets and life and us. When we say a magnetar is 10,000 light-years away, what does that mean? Light, the fastest thing in the universe, traveling at 186,000 miles per second, would take 10,000 years to reach us from that magnetar. If you set out toward it at the speed of light when human agriculture was first being invented, you would be arriving just about now. When we say a quasar is 1 billion light-years away, we are talking about distances that dwarf even the intergalactic voids. 1 billion light-years, 1 billion years of light travel. That is roughly 7% of the entire age of the universe spent in transit. The light we see from that quasar left when the first complex multicellular life was just appearing on Earth. These distances are what separate us from the dangers we discussed. They are so great that even the most powerful phenomena become harmless by the time their effects reach us. And within those distances, there is time. Time for stars to form and die, time for planets to coalesce, time for life to evolve from simple chemistry to wandering minds. Time for civilizations to rise, ask questions, and perhaps find answers. We exist in one of those pockets of time and space where things are calm enough for complexity, where water can exist as a liquid and carbon can form long chains and evolution can work its patient magic. The universe is a place of contrasts, dramatic and peaceful, destructive and creative, ancient and constantly renewing. The same nuclear reactions that power stars and could sterilize planets also forge the elements that make life possible. The same gravitational forces that create black holes also hold galaxies together and keep planets in stable orbits. We have evolved to perceive a very narrow slice of reality. The scales we encounter in daily life, from the size of insects to the size of mountains, from the duration of heartbeats to the span of human lives, are the scales our intuition understands. Everything we have discussed tonight operates on scales far beyond that narrow range. Distances measured in light years, time scales measured in billions of years, energies that dwarf anything in human experience. And yet we have found ways to understand these phenomena through mathematics and observation, through telescope and satellite, through theory and experiment. We have extended our reach far beyond our evolutionary heritage. We can comprehend, if not fully grasp, the magnetic fields of magnetars and the event horizons of black holes. This is one of the remarkable achievements of our species. We have built a picture of the universe that is vast and strange and wonderful. We have discovered that we live on a small planet orbiting an ordinary star in an unremarkable corner of a galaxy that is one among billions. And somehow, that knowledge makes our existence more precious, not less. The scientific enterprise that has revealed these cosmic wonders is itself remarkable. It has required centuries of patient observation, brilliant theoretical insights, technological innovations, and international cooperation. Telescopes on mountaintops and in orbit, particle detectors deep underground, gravitational wave observatories with arms stretching for miles, all dedicated to understanding a universe that does not owe us any answers. The people who study these cosmic phenomena are not driven by fear. They are driven by curiosity. They want to know how magnetars generate their magnetic fields, how black holes form and grow, why gamma ray bursts happen, and what the ultimate fate of the cosmos will be. The answers to these questions have no immediate practical application. They will not cure diseases or improve crop yields or make anyone wealthy, but they satisfy something deep in the human spirit. We are a species that asks why. We look up at the night sky and wonder what those lights are. We develop tools to see further, measure more precisely, and understand more deeply. And with each new discovery, we find that the universe is stranger and more wonderful than we had imagined. The cosmos is wild and strange and beautiful, and we are here to witness it. Good night.